Welcome to our first lab, which is going to be dealing with topographic maps. Now, a map is a representation of a physical place. And so when we're dealing with most maps, we're going to be dealing with how does place on Earth represent to a piece of paper? And in doing so, we're going to need to find a reference point, and we're going to be using longitude and latitude to do so. Latitude, as you recall, are the horizontal lines that run north or south of the equator, and they're measured north of the equator or south of the equator. So they're always going to have an N or an S associated with them. Longitude lines are measured off of the prime meridian, and they're going to either have an east or a west associated with them. And so here's an image of a topographic map in Arizona. And you'll look in the upper right-hand corner, and let's see if I can. Oh, oh, let me go back a slide. Sorry about that. You'll notice that on this map, they have 36 degrees, and they really should put again north in here, but topographic maps in the United States typically are going to be west of the prime meridian and north of the equator. And so we could put those numbers in there. If we look at a map like Google Earth, here's a map of the college, you'll notice that they do in fact give that information. In addition, they also have the elevation at the college here. And again, so we're located about 37 degrees north of the equator and about a quarter of the way across the Earth, 90 degrees of the 360 from the prime meridian. So any point on Earth is going to have a unique longitude and latitude, and those are always going to be identified on the map. So here are some of the key terms that we're going to be dealing with in this lab. And so we've already talked about longitude and latitude. The prime meridian is, again, a line that runs from the North Pole to the South Pole and the starting point of longitude and latitude, and the equator. So what we're going to be dealing now is with scale. And so when we start looking at a map, many maps are going to have multiple scales on here. The first one is going to be this one dot dot some really big number, and that's known as a fractional or a ratio scale. And that's how big is it on the map to that same number of units on Earth. And so in this case, 1 inch on the map is equal to 24,000 feet on Earth. What I just said there was the lower scale, the verbal scale. And then the last scale is the bar scale. Now, the advantage of the bar scale is if you zoom in or zoom out, the bar scale would also go increase and decrease. The verbal scale is useful in that we know what it is pretty easily. And then the ratio scale or the fractional scale is very useful in that it is not bound to any one unit. And so if we're dealing with inches, or meters or centimeters, it is independent of what units you're dealing with. And so each one has its own purpose. So the representation or the the RF scale or representative fraction scale or ratio scale, it's again a map of how big it is in the map to real life. And so you'll see that the bigger the number, the bigger the area you're dealing with, or the more zoomed out you are, if we're using more Google-friendly terms here. And then the more zoomed in we are, it's going to be a larger scale. Again, the denominator is going to be smaller. So the last part of the key terms are going to be the ones that we're going to be dealing with a lot when we start actually physically doing the lab. And so these are things like contour lines and contour intervals, relief, profile, vertical exaggeration, and hatch marks. So a topographic map is a map showing elevation. And so in this depiction, the upper image is a three-dimensional kind of showing a drawing of what we're going to be mapping on the bottom. What we have here on the bottom is a topographic map. And you'll notice that each one of these lines on the bottom map there represents one unique elevation. And so a contour line is a line that shows um, uniform elevation. And so if I were to look at the Earth right now, 0 degrees or sea level would be the 0 foot contour line. We call that the datum, or what we're measuring off of. In fact, we are in fact using sea level. And in this map, they're going up by in increments of 100 feet or 100 units. And so each contour interval is 100. You'll notice that these contour lines never split off. Where it's really steep, they're close together. Where it's flat, they're far apart. And they never just die out. Here's an actual image of one of these contour lines. And so we can see right in this area, the contour lines are far apart, and that means it's relatively flat. Over here, we have a very steep area. Really, really steep over here. I also want to talk about this river. Now, if we start looking at this map, if we labeled every single one of these lines, it'd get really messy. And so they label every fifth one, and that's called an index contour. And so from index contour to index contour, the elevation change is 200 feet. There's 5 lines in between, this line and this line. And 5 divided by 200 would be 40. So each one of these contour lines is going by 40 feet. If we start looking at this river, the elevation here is 5,400 feet. The elevation right here is 5,200 feet. And we know that water flows from big numbers to little numbers, or water flows downhill. And so we can confirm this. This is the 5,000 foot contour line. And so the water would flow from high numbers to low numbers. Now, as water is moving down, it'll start to notch out, it'll start to erode. And each one of the contour lines, you'll notice, have these V shapes. This is in topographic maps, it's called the rule of V's, and the V's point uphill. Water flows downhill. So over on the lower portion of this map, the southeast portion of this map, the water would be flowing in this direction. In a later lab, we're actually going to be dealing with something called a drainage divide, areas that would separate water from flowing from one direction to the next. So contour lines never cross. All points on one contour line must represent one elevation. Contour lines that are closely spaced means steep slopes, and far apart means it's flat land. I've already mentioned the rule of V's, and so we can see it playing in this area. These little triangles here tell us that the water is flowing in this direction. We can see that we have an elongated hill over on the left portion of this map. I do want to draw your attention to the right portion of this map, where we have these little negatives or hatcher marks. And in this case, you can see that the hash marks tell us that we're going down in elevation. If we didn't have those little hash marks, you'd end up with it would look like a hill. And if we didn't look at the contour lines and see that they were in fact negative, going down. So one portion of the lab is actually going to be dealing with drawing in your own contour lines using data points. Now, let me draw in, we have a river here, and this river is flowing from big numbers to small numbers. So it's going from the left to the right of this map. And it says that we should be drawing a contour interval of 50 feet. Now, starting at 0, because we always are going to start at the datum or starting point, we know that we're going in increments of 50. So you should never have anything that doesn't end in a 50 or a 0. And let's see, the lowest number we have on this map is 752. And so the next contour interval would be 750, 800. And so what you're going to do is you're going to try to find where the 800 dots would be. Well, I know that this dot, or this elevation in the upper right-hand corner is 780, and this is 1,103. And so 800 would be somewhere right around here. In between 831 and 870, 800 line would be somewhere. I'm just approximating. You might have it a little bit further left. I know that if I'm drawing my 800 line, it's going to connect points that are going to divide the map. Everything on this side of the map is going to be less than 800. Everything on this side of the line is going to be greater than 800. Now, I know that I have an 800 dot right over here and here. And I know that because if I'm going from 752 and walking up to 800, somewhere along the line, I'm going to hit that 800 line. Now, you will recall that we have a blue stream here. And this river, the contour line needs to create that V shape to follow the river. And so if we're walking along the river, here is an elevation of 752, and along the river up here, it's 831. And in between there, I'd hit 800. Now, I would always label these so I don't get confused. The next line would be 850. I know that I would have to go somewhere in between 860 and 847. So I could draw my 850 line somewhere in here. Connect these lines. Whenever I have the river, it's going to cross, and so that would be the 850. So the 900 line, that 950 line, it's going to have to either go up like this, the 1,000-foot contour line would go somewhere like this, and I can easily check any one of my work, all of my work, because if I take a look at this 900 contour line, everything on this side is less than 900. Everything on this side is greater than 900. Now, your line might look a little bit different, but it's still going to follow those same rules. Here's what it looks like if it was fully completed. And I'm going to extend these lines out. We don't have enough data over here to really understand what's going on beyond these dots. They could either wrap around themselves so it could go over here, but it just can't stop. And so it could have easily wrapped around over on this side, creating a little hilltop. Now, here's a map that has the contour lines drawn in. And what we're going to be doing on this last portion is showing a profile or a side view. And you'll notice that when the contour lines are closer together, it has a steeper side view or steeper slope. And so that's what we're going to be doing here is we're going to take every elevation, drop a line straight down and graph it. And when we do, what we end up with is a side view of the map. Now, if you're using Google Earth, it actually does, you can actually draw a path in, and then if you right click on this, it would say show elevation profile. So you can actually automate this quite easily using a program like Google Earth. And in a later lab, we'll actually look at some things like that. So what you're going to be doing on this one is you're going to have to, on this lab, you're going to be finding the elevation here is 10, go straight down and put in an elevation of 10, and then a 20, 30, 40, 50. And so if we were to walk from A to B, you'd walk up this hill and you'd walk back down, go up the second hill and go back down. To calculate gradient, what you need to do, just like in a math class, it's the rise over the run. And so the gradient from X to Y, the change in elevation is 80. So that would be a difference of 80, I'm going to just assume that they're feet per, oh, if I take a look at my little bar scale on the bottom here, I see that it is about a 1 mile distance between X and Y. So 1 mile. So the gradient of this should be 80 feet per mile. And again, units are important there. Yes, you could convert this into feet per feet and have it a unitless number. But as long as we list what the units are, we're in good shape. And so the last thing that we can do with this is take a look at some of these gradients. And if we use the same scale on either side, a vertical scale and the horizontal scale, we don't have any vertical exaggeration. But in many cases, the Earth would look perfectly flat or perfectly rounded without showing much hills and valleys. The more we exaggerate, the more change in elevation we're going to see on a map. And so very commonly, what we're going to end up with is a vertical exaggeration. In this case, we're exaggerating it 2 times because the vertical scale is twice that of the horizontal scale. And it's just a matter of comparing the vertical scale to the horizontal scale. So if you have any questions about this lab, please let me know. I just wanted to give you this little tutorial to make sure that you're in good shape for the lab.